We would like to take you through the rationale of this competition, why it is important for not only the social sciences, but in particular for investing. And in order to do that, I think that it would be very valuable if Professor Hernan could explain why causal inference is important to the sciences in general, what sort of questions is trying to address.
Sure. Thank you, Marcos, for giving me this opportunity to talk about causal inference, which is my favorite topic, as many of you know. So when we talk about causal inference, we're talking about questions that start with what if? What if we do this rather if we do this, right? So that is a basic question for science, but also for any human activity that involves decision making. We always have different courses of action, and we have to know what are the expected outcomes under each of those courses of action to make a decision. That's causal inference. So that is one important component of causal inference. And that is what many of us have worked on, methods for causal inference using non-interventional data, because of course it's easier to make causal inference if you can experiment and you can intervene. But for many questions in the sciences and real life and in finance, we cannot conduct experiments. So we have to use the data that we happen to have to make causal inferences about future actions. There are many successes in science. I work on health, so in the health sciences, in medicine, in public health. There are many examples of how this data has been, how the non-interventional data has been used to generate evidence that was used for decision making. One thing that you can, I'm sure that you all have in mind, is the comparative effectiveness and safety of COVID vaccines during the COVID pandemic. A lot of the evidence there was not coming from experiment, was coming from a clever use of electronic health records and other sources of observational data. But that is a big component of causal inference, but it's not the only one. There is another way of thinking about causal questions, which is rather than we have a causal question, we know we're asking the question, what if we do this versus we do that? And then we use data to answer that question. What if we have data and we want to use the data to infer what are the causal relationships in the data? That's a different type of approach to causal inference using non-interventional data. That is known as causal discovery. And that's what we're going to be talking about here. So rather than our starting point is a well-defined causal question, we start with data and trying to get from the data information about the causal structure of the variables. This causal discovery field is relatively newer, is also very cool. There are very intelligent, very elegant results there, but it is in its infancy in terms of application to real-world data. And that is why this type of competitions that we're going to hear about now are very important, because they bring to the forefront an open question that is very complex, is very hard, and definitely needs more work on.
Wonderful, wonderful introduction. Now, as you very well know, randomized controlled trials are the gold standard for answering causal questions in the experimental sciences, in particular in the case of medicine, but in many other situations. Now, this is not always possible in the social sciences. We cannot repeat the situation of, let's say, the great financial crisis and try different treatments and controls and see what would happen, right? In particular, in the case of social sciences, we cannot always, and in fact, very few situations, we can conduct randomized controlled trials. And that's where the work of Professor Imbens has been truly revolutionary. How can we answer causal questions when these sort of randomized controlled trials are not possible? One of his incredibly groundbreaking contributions was in the context of what is called natural experiments. A natural experiment is an experiment where nature does the random assignment of treatment and control. And in that sense, to understand the magnitude of his contribution, it opens an opportunity to answer questions in economics just like we could answer questions, for instance, in physics. It's truly transformational when you think about it. For many decades, econometrics was a way of running some regressions where the specification was not well understood, and these answers were very much biased by the researcher's choice. And part of the contribution of Professor Imbens was to introduce this objectivity, but I will let him explain much better why causal inference is changing economics.
Thanks, Marcos. So actually, I want to reflect a little bit on the competition part here of the ADIA Lab causal discovery competition. Kind of for much of the 20th century, kind of the scientific process kind of was very heavily focused on publications, on journals, and peer review. And I think what the competitions we see here, and we've seen in much of computer science in recent years, have done is really partly change that and open things up much more. And so in the standard kind of in the journal process, you would have an idea, you would do a study, do some experiments, you would send that to a journal, and then journals would decide whether this was good enough or not, and they might decide to send it out for peer review. I'm the editor of one of the main economics journals at the moment, and so I do that on a daily basis. And sometimes I decide that a paper just isn't nearly good enough, and I'm not even going to send it out for peer review. And that's to some extent a very subjective decision. Recently, actually, I got a paper that was arguing, so I had a very unusual idea. It was arguing that most of economics was actually very misguided. We were partly building these models that put some value on the future relative to today. And this paper was arguing that we put way too much value on the future relative to the value we put on utility today. And so if you took that seriously, it would actually say that we should not put very much value on tomorrow or next year. We shouldn't really worry about things like climate change. And it seemed a very unusual perspective. And so, but the idea in this paper was that, well, there's going to be some chance we were going to figure out time travel. And then we could just come back and clean up whatever mess we made. And so I said, well, that's a very interesting idea, but this may be for a different type of journal. And I couldn't resist, and I said, well, in the end, because maybe I'm wrong, but if I'm wrong, then it's not a problem, because I'm just going to come back in the future and publish the paper anyway. But the problem, of course, is these are all just judgments, and what is really nice about the way these competitions are structured, and they've been structured in computer science, kind of with these benchmarks where we try to see how well people can recognize handwritten digits, and you allow these competitions to bring objectivity to the whole process, and you kind of see what is actually working in a way that democratizes the entire scientific process in a very important way. Now, that's very hard in causal inference, where often we don't have the ground truth very readily available in a way that makes it easy to do competitions like the Netflix competition that got a huge amount of attention. And so what is really important here is that we try to set up these structured competitions where we can try to make progress in a way that makes it less subjective, and that can open things up for very unusual ideas, even though at first they may not resonate with people with established views on these things. So that's why I think it's just incredibly important to find ways of having these competitions in all areas.
Fantastic. Now, going down from public health, science, experimental sciences in general, to social sciences, to the particular problem that occupies us today, which is causal inference in investing. Why is this important? I referred to that during my presentation yesterday, and I made the case that causality is a necessary condition for efficiency. Unless you know what is the causal mechanism, or suspect, or have some idea, some vague idea of what is the causal mechanism underlying the data generating process, you cannot really control for certain risks. And investing is not really a forecasting problem, it's a problem of making decisions under uncertainty, where those decisions need to take care of controlling for certain risk exposures. That's where causality comes in. This is how we designed the tournament to answer this particular question. Now, there are two very different approaches that you can take for that. One of them is, as Professor Hernan explained, you draw your graph, which represents your causal assumptions, and then derive what is the specification that allows you to close all those non-causal paths so that what remains is the effect that you are trying to estimate. So that's, in principle, the way econometricians should inform the decision of a particular specification as opposed to another. Now, there is a second approach, which is we may not even have an idea of what is the potential causal graph that we need in order to close all these non-causal paths. So what do we do then? That's where the competition comes in. We wanted to encourage the community to produce causal discovery algorithms that are able to identify graphs that are consistent with empirical data. The answer is not, this is the ground truth, or this is the graph that is responsible for the observations, but to reduce the options, the possibilities, from millions of possible configurations to perhaps a few hundreds, or if you are lucky, a few dozens of graph configurations that are consistent with the data. And from that, the researcher needs to make a choice. But this choice will be transparent. The researcher will say, and this is the graph that I had in mind when I developed this investment strategy. And this is the graph that I had in mind when I did this regression. So that's really the contribution of this competition. And in that sense, it's the first of its kind. We look around, we try to see if there was another competition that could help us design this one, and the reality is that we couldn't find anyone. Most competitions relate to either design of experiments or forecasting competitions, but a competition that allows us to rank the performance of causal discovery algorithms, that's something that apparently is new. And so we are very excited. At the same time, we were also very afraid because we didn't know what response this would have. And as Emmanuel is going to explain in a moment, the response was quite amazing.
Yeah, thank you, Marcos. Yeah, I'm starting to, let me see if I can start from just defining the problem. My role today is to just explain the basics and go into the details of the competition. By the way, this is not just a work that I did by myself under the guidance of Marcos and with the other professor, but there are other two colleagues of mine, Vincent Zunikin, Patrick Yam, they couldn't be here today, so I have to share the honor with them of helping ADIA Lab in doing all this. But a few words about the specific of this competition on causal discovery. So we have observations. So you can see here, we have 1,000 lines, 1,000 rows, 1,000 observations of 5 variables. And exactly as Marcos said, what is the causal relationship between them? We can, let's say, draw a graph and say that X causes Y, and that's the arrow. Or 1 causes X and Y. Or 2, the variable 2, is independent, is not related to these other variables. So the process of going from the data, from the observations, to the graph is causal discovery, specifically also for this competition. We have plenty of observational data because we can look at the past, at everything we have collected. It's not a new experiment that we design. So that is why it's important, and as Professor Renan said very clearly, this is an open problem. The way in which we evaluated the participants on this kind of problem is interesting because the variables, and I'm spending a little bit on the details because it's important to understand what comes next. The roles of the variables in this graph are, let's say, just a few categories. For example, variable 1, that causes both x and y, the treatment and the effect, is called confounder. Variable 2 is called independent because it's independent of the other. Or variable 0, which is caused by x and y, is a confounder. And
collider.
The different, it's a collider, sorry. Thank you, Marcus. And by the way, Marcus, 2 days ago exactly made a presentation of how important it is to know in your models whether you have a confounder, whether you have a collider, what is what, because you have to include it or exclude it in your model accordingly. And if you don't, you have bias. Exactly your presentation of 2 days ago, which basically is tightly related to this competition. So the competition in the end was about finding out what is the exact role of this variable. So if you say variable 1 is a confounder, you did right. And instead, if you say it's independent, you did wrong. And it was basically an accuracy on how accurate you are on detecting the role of these variables. But of course, the graph is white on, maybe it's a bit better on that screen than this one. You cannot just do it from one data set. As in every competition, you ask your participants to, in this case, estimate the causal relationship, the graph between the variables, not one time, but 25,000 times. 25,000 data sets, 25,000 graphs. Why we need so many? Because we want to evaluate accurately what is the difference between one method and the other. If we use just 10, it could be just chance. But if you use 25,000, we are certain of the result. And since we face a data science community that is used to participate to data science competition, usually through machine learning methods, which is a sort of new trend inside causal discovery, we also gave a train set. So a set of data sets, again, other 25,000 data sets, but together with their actual causal graph. So as examples, so that algorithms that learn from examples, in case the participants wants to develop a method based on, for example, machine learning or supervised learning, as examples to learn from that. But this, of course, is a choice. If we look at the literature on this problem, the scientific literature, there are approaches that use examples and approaches that do not use examples. So we gave, let's say, breadth to both these directions. And of course, where do these data sets come from? This is a difficult question that was addressed in some ways by what was said before, and it was part of the discussion in the first part of the year. We had several meetings, several hot discussions, I have to say, because it's complex. So imagine if you design a system in which you have the variables, then if you have a model, you design the system of a model, you may not have the real data. And if you have the data, you may not know what is the exact causal relationship. So we need to strike a balance between them. We explored the literature and what are the typical ways to create these data sets and graphs. So you can have random graphs. You can have random functions that when you have a graph generates data. You can use large graphs that are available in the literature and just take pieces of them so that to simulate what could be a real graph that you have in nature. Or you can use even mechanistic models, you can use large language models. We really tried and explored many different avenues. I don't have the time here to explain exactly all the 50,000, by the way, data sets how they were generated, but we will detail this in a report that we want to prepare because we had many times this question, where do the data set come from? Data set and graphs. So at this point, we had this data set. We have a way to score the participants. And on August 1st, approximately 3 months ago, the competition started. And our partner, CrunchDAO, was hosting the competition. So maybe they want to say something about the analytics. How did it go in terms of popularity and success?
Yeah, thank you, Emanuele. So obviously the work started before August 1st because we had to completely readapt to kind of fit this new kind of challenge. The community at CrunchDAO is composed of about 7,000 machine learning engineers, but they are mostly used to supervised learning challenge, right? You mentioned the Netflix competition before that was very influential in the field, but it was really a new concept. The fact that there were 25,000 data sets, for example, the fact that it could be looked from different aspects, supervised, unsupervised, and etc., was very new for everyone. So we had to prepare a lot before, and we had maybe 1 or 2 months of active discussion as well to make sure that things will actually work and will be fully functional for people that are used to another kind of competition. And we were pretty successful at that, and we were really impressed at how the community welcomed this competition. And if you go on the next slide, Emanuele, we have the number of registration on the platform for this particular competition. So we reach more than almost 2,000 participants, so 2,000 people that join Crunch to specifically work on causal discovery here. And actually what I was really surprised about is that a big portion of these people actually came for causality. So I think they found something that were maybe missing somewhere else. And what they are really looking for, I mean, what people from the community are looking for is subjects that are not yet solved, right? If a solution is already somewhere, I don't know, in some repository or Hugging Face, or if it's already solved, it's not very interesting to organize a challenge around that. So seeing this new subject, I think, was really important in bringing awareness around what we did, and the participation of professors here today actually really helped drawing a lot of attention. In terms of active participation, we received, on the next slide, Emanuele, we have about 3,500 different models that have been submitted to the platform. And so the way people participated on challenge in Crunch Lab is they actually submit code. So they don't only submit prediction, they submit code. And what is great about that is that on the back end, we have the chance to test their code. So we can run it with out-of-sample data, we can test them on different predictive regime and etc. And it's a way to make sure that the models are going to generalize well and that are actually properly built, that are deterministic, for example, and all this kind of tests that you want to run. And on the last slide, that's the geographic participation. And as you can see, we had participants, maybe it's not very clear on this screen, but from a large portion of the world. So with a leading participation from the US, India, China, and Europe. And I'd like to thank particularly Ivy Wang, that have been really instrumental in helping us reaching to the university in China, which we are not present in last year challenge.
Okay, thank you so much, Sean. So going from the map of the world where the participants live, let's go to another map. This is the map of the submissions, or the map of the solutions. Of course, this is not a geographical map, but you may imagine that as data scientists, what we do is to take these 3,343 submissions and try to make sense of it. So this map, this is one of the main contributions of Vincent that collaborated with us, is a way to look at them. We can summarize using large language model the code of each solution in a short sentence, in a paragraph. And we can do this 3,000 times. then we can, I'm saying some technical details on this one. We can embed these descriptions into a vector. At this point, these are just a string of numbers. And when we have that, the data scientists are happy because they can do clustering, they can do a lot of things. And in this case, using one of the clustering algorithms, we can create these islands. And then within an island, we can again use large language models and try to give a name to the island. And so we see some interesting structure. It's very detailed. Now I'm going to explain a bit the interesting parts. So let's look at the bug, for example. So every, let's say, every circle that you see here is a submission, is a piece of code that runs on the cloud, that produces a solution to this problem. And as you can see, we have neural network solutions. We have the island of machine learning pipelines. We have the staple, the pillar, I would say, of causal discovery, which is the PC algorithm, and many others. If we go a bit on the north of this map, okay, we see these tiny islands. I would say that these are among the most popular methods in the literature. It's quite accurate, I would say, that received attention. So one of the goals of this competition is also to have a survey on what are let's say, the most known and used method for causal discovery. But let's go back a bit and let's focus on what was successful. So if we filter all these dots, these 3,000 dots, to what receive a very high score, we can see just a few of them, and just some islands in this map make sense. Let's focus exactly on where there are, let's say, solutions that could rank in the first, let's say, 20 places. And if we focus even more on super high score that could make it in the top 10, we basically see that only a few islands could make it. And basically here we have neural network-based solutions, again, supervised learning from examples. We have machine learning pipelines, solutions, and again, the PC algorithm, some other solutions, and a tiny island, Ensemble, Avicii, and Exact Search, an algorithm that I didn't know even it existed. So one nice thing of this competition is even to discover ideas that are already there, but there are so many that you cannot, let's say, know them. Of course, this island didn't come out of nothing. We sort of seeded the map in some way. We prepared some baseline solution based on neural networks, based on more traditional machine learning, so creating features using, I don't know, gradient boosting or tree-based methods, or relying, as you can see on the right, on traditional unsupervised algorithms. And you can see that basically all the top solutions come from, let's say, two islands mainly. And we will see that, in fact, for the top solution, this is everything that was submitted. The participant has to select, because some people submitted 60 solutions, 16 maybe slight improvement, one after another, but they have to choose at a certain point what was their actual one. So that is why we have many points here, but then the winning solution that we show today, there are just 10. And just to give you a quantitative idea of what we did, this is a baseline, so a tutorial solution, by the way, that I wrote in this case, that used traditional machine learning methods, so creating features, using standard classification algorithms in a new way. By the way, I didn't find basically literature on that. I had to invent a method. But I wanted to make it simple, that can run with very limited resources, so that participants would be inspired with also descriptions of step by step from the formulation of the problem on how you do this using a notebook, using something that can be executed. And it was actually a solution. It's the one pointed by the arrow, by the way. The score that I get with that solution, okay, may not be my best solution ever, but it's around 40%. And you can see on the right side, on your right side, yes, that's correct, for each of the categories, confounder, collider, mediator, independent, what is the breakdown of the scores. It's not particularly high, as you can see, but this is basically what is the standard of, let's say, like the PC algorithm can reach on this problem. So we don't have yet, let's say, strong solutions for this problem of causal discovery. And these three different baseline solutions that we gave to educate the community on this problem and give them a hint on how to address the problem, because this is totally new, let's say, scored more or less on what is the standard algorithm in this field. All the three solutions and more or less this kind of scores. And then 3 months of work and 2,000 participants, let's say, did a lot of that. And now Jean can illustrate the winners of the competition, and you may appreciate how much they improved from the starting point that we set. Jean,
thank
you want even to come here?
Yeah, maybe I'd like to stand up to honor the work of the engineers and doctors that work on this subject. And so we decided to compile the top 10 submission and to present the profile of the best cruncher, how we call them, that participate in this particular competition. And I'm going to start with the number 10. So the number 10, congratulations, is named Team Nguyen. Team Nguyen provided a machine learning-based graph that already consistently overperform the benchmark that were provided with about 66.34% accuracy compared to about 40% in the baseline provided. So congratulations, Tin. This is an amazing work. But that was a bit expected since Tin is actually spent most of his life working on causality and innovating on the field. So congratulations, that was an amazing job, and he received the prize of $3,000 of the total prize pool. On the number 9, on the 9th position, we have Quang Duy Tran, which is a PhD student out of Deakin University that is also studying causality. He provided a solution that improves slightly the number 10 with 66.59%. And congratulations, Quan, because he's just starting his PhD and is focusing on causality. So that's a very good submission. Congratulations, Quang. And by the way, they are watching us live now, so these results have not been divulgated before, so you don't feel it, but there is 3 months of work on the other side of the camera. Congratulations, guys. On the position, on the 8th position, we have Gregor Tratovsky, who reached 68.62% with a solution that is between ML-based graph and an ML pipeline, more of a traditional approach, but that overperformed the other players. Congratulations. Gregor has a PhD in reinforcement learning. He is a senior quant researcher in the US. He works in equity at several banks and is especially focusing on time series analysis and reinforcement learning. So congratulations, Gregor, for this amazing job. On the place number 7, we have Bao Duong, which is another student from Deakin University working on causality. And as you can see on this graph, even if this group are coming from the same university, it's radically different submission than its colleague. And he actually outperformed his professor. So congratulations, Bao. He is also having an extensive background on computational techniques. So congratulations, Tao.
I think we got him in trouble.
Yeah. Sorry, Bao. Good job. On the position number 6, we have Jorge Linde Diaz. Congratulations, Jorge. So we have this participant coming from Europe this time, from Spain. And Jorge provided a solution that is in the very top cluster there. So he built a neural network, which is more computational intensive than the other techniques that we've seen before. And George has an extensive background. He is a doctor. He has a doctorate in mathematics science. He's a data scientist at Indra. He's also a professor at University of Complutense in Madrid, also teaching at CUNYF University, and he has more than 11 years experience in the field of machine learning and deep learning. So here again, we had a very, an excellent profile. And now we are in another category of price with $5,000 for this category of participant. Thank you so much, Giorgio, for providing this solution. That was amazing. On the 5th position, congratulations to Nu, which is another student from the Deakin University that provided this time an ML graph solution that reached 70%, 70.37%. Congratulations, Nu. She's also focusing heavily on causal research, and she did an excellent job. Congrats, Nu. Now we're getting on the very top of the leaderboard. We have Alexander Kishle-Cornish coming from Australia with an ML-based...
New Zealand.
New Zealand, sorry. With an ML-graphed structure models. That's also someone that have an extensive experience in computational techniques. He is a quantitative researcher at Optiverse. He's also a big competitor. As you can see, he's used to compete in this kind of event, and he really likes to provide his solution, and he's actually performing pretty well. He's also a member of the 2020 national team of rock climbing. So congrats, Alexander, for this achievement. It's pretty impressive. Now, on the podium, we have a team of, it's actually a multidisciplinary team coming from Shanghai Tech and Xiamen University in China. And now we are reaching 74.06% of accuracy in the data set. And that's really, really impressive. That was even unexpected to go there.
Yeah, if I can comment, especially in these top solutions, it's impressive the amount, the score, specifically for variables that are category variables that's very important, as Marco explained 2 days ago, confounder, colliders, mediators. If you remember, a standard in the field can be 20%, 40%. Here we are talking about 60%, 70%. So it's dramatically different. Okay, the problem is, we could question about many things about the competition, but the improvement is outstanding, especially in these super top solutions.
Yeah, absolutely. And so we've seen this number going up, by the way, along the competition. And I think there is also part of the collective intelligence aspect of things that you already mentioned before. That is really important when people can exchange in the forum, in the chat, try to iterate toward better solution, find what works, what doesn't work, and etc. It's really important in this framework to have both competitive and collaborative things that happens to make sure that you converge toward the best possible solution. And what's interesting in this team is that it's actually multidisciplinary. We have a major student at Shanghai Tech that is majoring in computer science, focusing on bioinformatics and AI. And his partner is from financial engineering at the Xiamen University. He's also a competitive data scientist. He already won some prize in different competition. But here, I think the multidisciplinary aspect probably helped them in converging pretty well. So congratulations, guys. That's one of the top pool prize on the 3rd position. That's excellent. Now, for the 2nd position, we have another team, André Franca and Alexis Gassman. For those of you who were here last year, you maybe recognize one of these two names because Alexis was one of the winners of last year's challenge, by the way. So he's really an outstanding member of our community. And we have André, by the way, which is in the room somewhere. Congratulations, André. I think we can clap. Congratulations, guys, for this amazing work. We are at 74.47%. So we start to cover slightly. But what is very interesting about this submission is the fact that you guys provided a unique cluster. that is pointed by the arrow here, with unique techniques that both outperformed the other techniques, but was also innovative. And we actually compiled a small video of you guys presenting that we will play a bit later, after, of course, talking about the winner of this competition. But first, on their background, André is theoretical physicist. He was he actually did a lot of work already on causality, right? You were VP of Research and Development at Causalence, which is a famous library out there. You were Executive Director at Goldman Sachs, and now you are launching your own company called Ergotic AI, and I wish you the best luck for this venture. Alexis Gassman is a competitive mind as well. He's spending a lot of time in competition, and is also a Kaggle competition expert. If some of you heard about this platform, other competition used to be run there. Now, and without further ado, the best solution of the causality competition this year was from Isham Alak. Congratulations, Isham. I think we can all clap for this amazing work. Unfortunately, Isham couldn't join us today, but as you can see, he built a solution that is a neural network, and that completely blew all the other solutions. So absolute amazing work. 76.70% was the best performance this year on the out-of-sample dataset.
I can even add maybe a technical note that what I found interesting is the use of convolutional neural network that is typically used in images for causality, which is a problem which is completely different. So I don't know all the literature, of course, in causal discovery, because it's difficult also to know everything. But I think this is also a new idea in that direction, and we are looking into it and discussing with Isham to better understand what he did.
But it's amazing work, and it's really different from the other submission as well, by this fact of using convolution networks, which is really surprising on this subject. So, and it was the first competition of Isham, so congrats for putting also a fit in this field. But Isham has a background. He is an engineer from École Centrale, which is one of the best engineering school in France. He has a second master in data science from Télécom Paris Tech, which is also one of the best engineering school in France. He has more than 10 years of professional experience. So we have someone that spent a lot of time with real use case and implementing solution in the real world. He specialized in recommended system and customer segmentation models, but he never worked on causality before. And I think this is what also is the beauty of this kind of competition, is that we can draw talent to subject and kind of make new people getting interest into this field. And Isham will never have built anything in causality before if we would not have organized this competition. So that's I think, a very good outcome. So congratulations, everyone, especially to the top participant. I would like, before getting a word from the participant, and especially from André, that commented this solution, I would like to acknowledge maybe, I think we don't have the next slide. Yeah, okay, here it is. To acknowledge the help of the people that made that competition possible, from the ADIA Lab team, so Marco Lopez de Prado, Guido, Miguel, Emmanuel, you've been instrumental in helping us putting that together. Thank you. Thank you from the ADIA team with Emmanuel, Vincent, and Patrick that also helped us a lot in this construction. From the crunch side, we had people that really moved a lot of things. Enzo, Max really helped putting that together from my team. On the ADIA Lab side, Amélie Koch, Humaid, Abdullah, thank you so much also for your help for putting that together. And finally, Alexander Molak and Ivy Wong have been instrumental as well in reaching more people and making this competition a complete success. So thank you for making that possible. And finally, the last word is for the participant. Can we play the video of Andre?
Hi everyone, I'm André Franca, CTO at Ergotic.ai, and I'm here to talk about a solution that Alexis Gassman and I did for our submission. So we did a mix of two different approaches. The first approach was using some or modifications on already established causal discovery algorithms. I'll go into more detail. And the second approach was using deep learning method, a novel deep learning method. And then at the end, we built our own infrastructure to actually assemble these together. So to go into more detail, right off the bat, most of the out-of-the-box solutions for causal discovery just didn't work very well on this data because this data is full of linearities, non-linearities. Of course, the noise of the data was kind of obscure because we're only looking at the copula. And then, anyway, there were a lot of technical challenges that made that out-of-the-box causal discovery methods not work really well. So our first part of the solution, we came up with our own pipeline that used PC algorithm, using a nonlinear transformations on the data to actually create a conditional independence test that was coming up with a much better skeleton than what traditional PC was doing. So then we use our own modification of an A-star search algorithm, again with a completely different scoring function, to actually come up with orientations on top of that skeleton. But that was just enough to get to 68% or something, which is still a bit far from what the state-of-the-art algorithms in this competition ended up. So then so Alexis and I, then we used a deep learning approach, which is based on a model called Avicii that uses a variational autoencoder to fine-tune on the data to actually come up with estimates of the causal graph. What was interesting is that there was a lot of orthogonality between these two approaches, which means that there was some opportunity to come up with an assembling method. And if you think about it, actually, you don't need to restrict yourself to these two approaches. You can throw in basically any causal discovery algorithm that you want on top of an ensembler. And then this ensembler, what it will do is that it will look at the characteristics of the data. It will look at, how many features you have, what's the, properties of the covariance matrix, some random matrix theory properties of the data, to come up with, a final, probability distribution on each one of these edges. And then what you can do afterwards is to reconstruct a graph on top of this ensembler and come up with a final estimate. And this is what we did. So ultimately, right, it was really, really challenging because it's a very nascent field. There aren't a lot of out-of-the-box solutions available. So we actually had to go and start from scratch and then think really carefully about what's present in the data and how we can make that surface out in the algorithms that we were building. So thank you very much, everyone.
Thank you. Thank you so much, and I leave the mic to you. Oh.
Thank you so much, and congratulations to all the winners. And I would like to thank all the participants and I would like to thank again the advisory board members, Emanuele and Crunch, for making a successful competition. We will have time for questions if you have, before we move on to the
Just a quick question with regards to Henan. You did mention that within the field of finance and economics, there is a challenge that we cannot have a pure experiment. I was wondering, the work by Daniel Kahneman and Fair as well, in trying to test trying to test some of the assumptions that we have in economics and have these synthetic lab experiments, is that not considered as a viable approach in trying to test these assumptions in the financial systems? And also, in terms of this goes back to Marcus' paper as of Monday or Tuesday, I believe. I'm looking at the distribution of what happened in terms of those who had the award. I realized that maybe it was fairly distributed across board. in getting to the final, maybe 66 and whatnot. But if I'm to follow your paper quite rightly, you did mention that the collider is a bit more dangerous. So in terms of distributing this weight, as in the accuracy they get across each, don't we think that maybe collider might get somewhat more, confounder might get somewhat less, and what's not? I think that would be it on my end. Thank you.
Thank you for the question. So one way of thinking about this is that we can make experiments for simple questions, but it's very hard to make experiments for hard questions. So if you want to know whether a treatment A is better than treatment B for this patient to see how the blood pressure changes in the next day, sure, we can make experiments. If you want to know whether a strategy that starts with treatment A and when the blood pressure goes up to a certain level, switches to B, and then if there is toxicity, you change to C, and you want to know what the effect on heart disease is over 5 years, it's much harder to do an experiment. And that applies to finance and to any other field. If the question is relatively simple, it's more likely that we will have an experiment. And I like, if I may, just to say something about how to link this issue about complexity with the competition that we were discussing here, because people have seen that the scores here are in the 70s, even the top one. In many other competitions, I'm sure that they get to the 90s. Mm-hmm. And you can say, okay, well, this is still not very good. But think how complex this problem is. This is a much more complex problem than supervised learning, a typical supervised learning competition. In the extreme, if I give you two variables, A and B, in the data set, and I ask you what is the causal structure, it's impossible to answer. I find that they are associated, but I don't know if A causes B, B causes A, if they have a common cause, if there is a collider somewhere that had been conditional, it's not possible to answer it. So here, by giving a level of complexity with 5 variables, with some structure and with some assumptions, we can start making progress in this problem. Of course, as things get harder and harder in the real world, the methods that we have now will work worse, and that's why this competition is very important. It's a first step towards getting closer to what the real world is.
And you referred to 2 other questions. You asked 3 questions, interrelated, very interesting. But you also mentioned whether the work of Kahneman and Thaler would also constitute causal research, and the answer is absolutely, it is. The difference between their work and the work that we are trying to do here, and of course the work that Professor Binz has done, is Kahneman and Thaler do actual experiments. They take subjects, assign them randomly to treatment and control, and see what happens, right? And they have done great progress in that respect in the context of behavioral economics. However, the problem that we face is different, and one might even argue more difficult, in the sense that we cannot conduct these sort of randomized controlled trials. We have observed data, and we need to answer causal questions from that observed data. So that's where Professor Imbens has done tremendous, incredible work in the context of, for instance, natural experiments, and also simulated experiments. So that's the second question. And then you asked the third question with regards to whether we should give more weight to colliders or as opposed to, for instance, confounders or mediators. Perhaps in reality, all of these are sources of biases. So you want to avoid all biases, whether they are confounders or colliders. The danger today is more on the colliders, because the textbooks are telling us to follow approaches that are not resilient. They are not robust to the presence of colliders. So that's where the danger is, right? The literature is well advanced in terms of what do we do in the context of confounders. But colliders appear to be more or less disregarded, and there are plenty of colliders in financial data sets. So that's where we need to be more cautious. However, we want to develop algorithms that are able to identify the entire graph. And that includes identifying confounders as well. But perhaps Professor Invens wants to comment a bit on the importance of natural experiments.
Yeah, so when I comment kind of on the sort of a couple of the things, sort of first the experiments in behavioral economics, I think those have been incredibly interesting, and they've really helped us understand some of the problems. But it's clear that in social science, the external validity of a lot of the lab experiments is a big concern, and whether the findings in these lab experiments actually work in practice when interventions are used on different populations isn't clear. Now, on the last part, sort of with the scoring question, I think that's a very tricky question, where we, in the end, think the most important mistakes are being made, where we think these models, the models are most sensitive, isn't quite clear, and that may vary a huge amount for the different type of problems. So this is a first competition of this type. I think we learn from looking at the solutions and kind of studying what methods people were using, whether there were aspects of the competition that ex post could have been done differently to make the competition focus on other more challenging questions. I think that's still an open question. In the end, kind of in much of social science, we can now do experiments. People actually do experiments in economics much more regularly than they used to. But we're always going to rely on observational data for a huge amount of the decision making, and trying to figure out there how we separate the spurious correlations from causal effects is still going to be an ongoing challenge.
Thank you very much. It was super interesting to be here and hear from all of you. Maybe just a couple of questions. There has been progressive movement. If you look, especially in economics, the literature has been moving from theory to empirics significantly over the past 10, 20 years. The main reason is that data is finally available big time. However, after hearing from you, it seems to me that it's also, there could be a shift back to theory to some extent, especially when you don't know the DGP of your data. Just to get your views of the importance of theory in disciplining, again, the selection of the variable, especially when in the real world, when there are so many things that are happening at the same time. And then the second question is, here I really, it's just to get your opinion on these things, but it may be also, there may be a state of the world in which causal relationships are endogenous, in the sense that they change their relationship over time. And I can think of financial applications in which, for instance, a certain causal discovery leads to identify some causal relationship, but because people start to invest in a certain way, the causal structure changes over time. And I cannot stick to the original model that I'd initially identified using the original data set, because this structural relationship have changed endogenously. I don't know how you see these things. Thank you so much.
Let me comment quickly on that. Definitely, we have to assume that economics being a dynamic system, the causal relationship will change, and the parameters will change. Even if the causal graph remains the same, the betas of the graph will change over time. Now, developing strategies that take into account the causal structure means that the strategy will be much more robust to changes in parameters. So for instance, consider, for instance, in a confounder graph. If you run some regression of x versus y, your beta is going to be biased. And the bias will be a function of the delta and the gamma, the two other parameters. So now, your strategy is impacted by 3 variables, not by 1, by 3. There are 3 points of failure, not 1, 3. In the case of a confounder, exactly the same. You will have 3 points of failure as opposed to 1. Now, that doesn't mean that the strategy is guaranteed to succeed. The strategy can fail, but it can fail for one reason, and one reason only. that that parameter changes, as opposed to developing a strategy. Now, this is an example with 3 variables. Suppose in an economic model where, in fact, you have 100 variables. Now, you are trying to profit from 1 variable. Now, instead of having 1 point of failure, you have 100 points of failure. So from that perspective, yes, it is true that economics is a dynamic system, but developing strategies that are causal allows you to bet your funds on models that are much more robust. And not only robust, but they are also prepared for what we might call black swans, in the sense that, yes, there are a number of effects that have occurred in the past, but there are many possible outcomes that are predicted by the causal graph that have never been observed. Now, if we develop a purely machine learning model that is fit to historical data, these alternative states of the world that have never occurred will harm the strategy, because the strategy is not prepared for what has not been seen. As opposed to developing a model that is theoretical, that takes into account those events that have never happened before. So that's a second layer of robustness that is introduced by causal reasoning.
So let me also make a couple of comments here. So the concerns you raise about the systems changing over time, that's something that economists have worried about for a long time. That often it's referred to as the Lucas critique in macroeconomic settings. If we change macroeconomic policy, that's going to change how people behave. Their actions are partly based on what they expect government policy to be, and you may change it in an unexpected way and find some effect, and that's not going to be the same if you keep changing it in that particular way, so that that becomes part of the expectations of how agents act. So thinking about economic theory, it's very important. That is, you know, that in some sense that is what distinguishes econometrics from statistics, that we do take into account the economic theory about how people behave. And to kind of make that very concrete, if you think about estimating demand functions, which of course is very important for a lot of the online companies these days, that is not just a supervised learning problem where you're trying to predict sales as a function of price. You take into account the fact that prices are not set randomly, but that they're set by sellers in a way that anticipates what demand is going to be. And so sellers anticipate the demand for children's toys are going to go up before the holidays, and so prices may be high at that point. That doesn't mean that if you actually increase prices, demand would go up. So we always need to take into account economic theory and incentives of any kind. You may not always see that directly in some of the empirical work, but it motivates the way we look at the data from the outset.
If I can make a couple of comments also about that. You raised two very important points. One is the role of theory versus data. And this is something that has been discussed a lot in the causal inference literature. When we know a system well, if we know a system perfectly, we don't need data. We can use theory. Think of any physical law where we don't need to do an experiment now because we know what the law is. In most examples, in health, in finance, in the social sciences, we don't have a perfect theory, so we need data. On the other hand, if the question is very simple, we don't need theory. We do a randomized experiment. There is no theory there. It's just data. So the relative weight of theory and data depends on the complexity of a question and how much we know about the system. And your second point is also very important, is how the causal structure may change, and that happens all the time. Let me give you a very current example. Everybody here knows about these magical weight loss drugs that we have now. The GLP-1s are being used. People lose weight, but we don't know why they lose weight, but it seems to have to do with the fact that it changed their eating patterns, that people don't feel the need to eat. This is having a huge effect on the food industry, because people on these drugs are eating less, are spending less money. The food industry is very concerned. If a big chunk of the population gets on these treatments, their sales are going down, because for decades they have perfected their products to appeal to people who are not on GLP-1s. So as soon as this is happening, what we are seeing now is how the food industry is changing and is doing research to change tastes and flavors for people who are on GLP-1. So everything that we have studied before about the effect of food on health will change because food is changing. And the only way to deal with this is to keep studying. We have to reassess things over time because causal structures change.